Well, what if we wanted to estimate the variance in the population so that we could use those equations to uh, come up with the appropriate sample size? One approach is to conduct a pilot study. So essentially, you're doing the research twice. The first time, you want to pull up a sample so that you can see what the variance in that sample is, and then use that sample variance to estimate how big your second sample has to be. Of course, this is expensive. You're, as I say, essentially doing the research twice. Normally, the pilot study is a smaller sample than will ultimately be used. And it does have some other value. It can be used as a pretest, so you can assure that you have all the right measures and that they're being understood and coded properly. A second approach is called progressive sampling. So this is where you conduct a survey. You're not sure how big the sample has to be. Once you've got 20 data points or 50 data points, you calculate the variance and you use that variance in the smaller sample to compute the ultimate size of the sample you need to do, and then you continue sampling until you get that sample size. This works very well for, particularly for internet applications where the data are coming in and can be analyzed in just a few seconds after they arrive. Well, how do we go about identifying our sample? There are various procedures. A convenience sample, sometimes called a judgment sample, is a group of participants that are convenient, so easy to recruit, easily available. The judgment comes in when the researcher or the manager use her judgment to conclude that the sample is appropriate. So if based on the manager's knowledge, he can look at a group of people and say, yes, these are similar to my target market, or these are the kinds of people that I'm trying to attract. And so even though they're convenient, they're appropriate to be included in a sample. Now, because they're chosen conveniently, one must generalize estimates from that sample to the population at some risk, because statistical tests presume that samples are pulled from the population with known likelihoods of being in the sample. So that's what a random sample is. A random sample is when every member of the population has a known likelihood of being in the sample. Simple random sampling means that every member has an equal opportunity. So drawing names from a hat or using a random number generator to select people from a sample frame are examples of random sampling. Quota sampling is done when the researcher expects that there are other factors at play. So earlier talked about control variables. These are measures that are taken because we believe that there are other variables that influence the dependent measure, and we want to measure those to control for them. Quota sampling and stratified sampling are done to assure that the sample has good representation of values of these control variables. So if we expect that our population is, say, 50% age 50 and above, and 30% age 30 to 50, and 20% below 30, then we want to assure that our sample also has the same proportion of those ages. The difference between quota sampling and stratified sampling is that quota sampling starts off with whatever procedure is done and counts the number of people in that group and then stops accepting them once the quota is filled. And stratified sampling identifies them ahead of time and then random samples from those groups until the number is filled. So stratified sampling is a bit more stringent in its production of a random assignment and is better for statistical purposes. And quota sampling is a little bit more like a convenient sample that simply has a representative that assures that the sample is representative on that variable. Proportional and disproportional refer to whether or not the sample has the same proportions as the population. So in the example I just gave, if the target market were 50% age 50 or above, the sample would be 50% age 50 or above. So that's proportional sampling. So you have the same proportions. Proportional sampling makes sense when you want the sample to be representative and you don't have any reason to think that subgroups should be more or less represented. But there are reasons why subgroups should be more or less represented. Sometimes subgroups are more important than others. For example, a manufacturer might be sampling resellers of his products, and large national chains might be few in number, so they may be a small proportion of the total number of resellers, but because they're very high in volume, they're much more important. And so a sample of resellers a researcher might want to include a higher proportion of national chains simply to reflect that importance level. Another reason for disproportionate representation is when the subgroups have different variances. So you can imagine three subgroups, one with a very high variance, one with a moderate variance, and one with almost no variance. Well, let's say the one with almost no variance actually comprises half the population. Well, because there's almost no variance in that population, it doesn't make sense to make half the sample from that group, because only a few members of that group would be a good representative sample, because they don't differ very much. You can imagine if they were all exactly the same on a given measure, you'd only need one representative to represent the entire group. Whereas the group that has very high variance should be overrepresented in the sample in order to reduce the error in that proportion, or in that subsegment. A final sampling procedure is cluster, and cluster is included here because it's done a lot in marketing when the population is geographically dispersed. Cluster sampling begins by randomly sampling groups from the large population. And in the most common application, these are area groups, and so sometimes this is called area sampling. So let's say that you randomly sample states or regions to represent the population of the United States. And then within those regions, we would randomly select a sample. So you could, if you assume that the states are a representative, each state is a representative group, as a group represents the United States. Now, of course, on political opinions, this would not be true, but on beliefs about Campbell's tomato soup, it very well might be true. So you randomly select 4 states, and then in each of those states, you might randomly select 50 consumers, and then you could administer a survey to those 200 people and reduce travel time as appropriate by simply making 4 trips to states rather than 200 trips to people in isolated locations around the country. So there are some biases that affect the quality of samples. One of these is accessibility convenience. Accessibility bias results when the sampling units that are easiest to recruit happen to be different from the population as a whole. Obviously, the willingness to volunteer to participate in a sample is an example of an accessibility bias. But it may also be that people who are simply located close to the research are different from people in the population as a whole. Affinity bias is recruiting people based on their relationship with other people who are recruited. So in a mall intercept, for example, if 4 people come by in a group and you ask one of them to participate, and then the others agree to participate because they have some affinity, some social connection to the first person you asked. And of course that means that you're oversampling from these sort of micro groups. Cluster bias is the bias that results in cluster sampling. Remember that the presumption is that those clusters are a representative distribution, or are a distribution that represents the total population. If in fact you were to choose a group that was biased to begin with, then all the members of that group are going to reflect that bias. Non-response, self-selection, and termination we've identified before as biases in doing survey research. You hope that the people who agree to participate and the people who complete the research are similar to the people who were not asked, or the people who refuse, or the people who do part of the research and don't finish. It's very difficult to be assured of that, but as mentioned earlier, one check on that is to take measures from the sample and compare them to known measures in population, measures of demographics, for example. Sampling frame order is a problem with taking a sample, having a sample frame that's in some order. Let's say it's alphabetical, and you want a sample of 100, and so you take the first 100 names. Now, for most marketing purposes, that probably will be a decent sample, but educational researchers, for example, have shown that people with names early in the alphabet tend to be more favorable about school and better students. And one explanation is that so much of education uses alphabetical lists that they tend to get called on more frequently. They're more likely to be called on. They tend to be seated in the front, and those things tend to help socialize them in positive ways about education. In marketing, a more common instance would be using a sampling frame that's ordered by date. So date of purchase, or date of registration, or date of enrollment. And you would expect that early entries on such lists would differ from later entries. And then a sample frame bias, again, we've mentioned earlier, sample frames are rarely 100% of the population, and the way the sample frame is constructed or defined often will include some bias, whereas by which some types of people will be more accessible and more likely to be on the frame. Finally, a short discussion of statistical errors. These are errors that result not because of biases in the sample, but simply because of the nature of statistics, and they're related to sample size. These statistical errors are referred to as type 1 and type 2 errors. A type 1 error is defined as erroneous support for an hypothesis, that is, an effect or a difference. So if you hypothesize that one ad is going to be more successful than another, or if you hypothesize that a sample with given characteristics will be different from the population, and that is wrong, that indeed there is no difference, or that the sample is not truly different from the population, then you've committed a type 1 error. Type 1 error rates are acceptable type 1 error rates are denoted by alpha, and as I said earlier, conventionally alpha is set at 0.05, sometimes 0.10, rarely different from either of those, although should back off on that. In medical research or in engineering research, alpha is typically set much, much lower. So the tolerance for a type 1 error in medicine may be 0.0001. Or engineering, I mean, you don't want to have a 5% chance that a bridge is going to collapse. Type 2 error is the erroneous rejection of a hypothesis. So it's erroneously or mistakenly concluding that there is no effect or that there is no difference. Type 2 error, acceptable type 2 errors are denoted by beta. Beta is most often set at 0.2. So that the conventional alpha level is 0.01, the conventional beta level is 0.20. And then finally, statistical power. Statistical power is related to the beta rate. Statistical power is sort of the obverse of beta. It's the likelihood that a study will detect a true given effect of a certain size. And it's expressed as 1 minus beta, and therefore the statistical power is typically set at 0.80. So that means that a typical research study has an 80% chance of detecting a true effect. So if alpha is set at 0.05, it means that we are 95% confident that an effect of a certain size is a true effect. And if statistical power is 0.80, we are 80% confident that if there is a true effect of a given size, that we'll find it.